All right, good morning. Today is the start of week 6 for us in geometry and is a new unit. This one's on right triangles and trigonometry. And then we have 2 more units to wrap up the materials for this term before we go to the final exam. I guess the good news, there's a unit test for this unit, which is technically unit 5. Then follows unit 6. There's 1 test for that. Unit 7 is on circles, and it's very, very short. There is no unit test for that one, and so that will roll right into getting ready to take the final. So we're at that point in the term where you probably need to make some notes on your calendars about when these things are due, when you need to have all your work finished so you're not jamming it all into the last week of the term. And if you want to retake any of the tests, you know, put that into your calendar also, and be sure to let me know. Some of these I have a second version of. Some I would just have to eliminate your other try and then give you the best score for whatever, whichever of the 2 is better. So you guys, what do you guys know about right triangles? Anything? A little? A lot?
90 degrees.
90 degrees, yeah. That's one of the things that makes them special. We also have some very specific types of right triangles that you probably will see. If you've ever heard of a 30, 60, 90 right triangle, that has some special properties. 45, 45, 90, those have special properties. It's, from one standpoint, though, it's just like any other triangle. They still have to, all the angles still have to total 180 degrees. And I guess if you're wondering about which angle is going to be the largest in a right triangle, well, it's always going to be the right angle, because that's 90 degrees, and you can only have one right angle in a triangle, because if you had more than one, you're already at 180 degrees. You can't do that. And then there's no room for the third angle. Hopefully that makes sense. So what this unit starts off with is the Pythagorean theory. Remember what that is, maybe?
A squared plus b squared equals c squared.
Yep. A squared plus b squared equals c squared. I don't know if you've ever thought about this. If you bought like a big screen TV, you know how they measure those, don't you?
From right angle to right angle.
Yeah, it's from corner to corner diagonally. It's not, they don't measure it along the bottom or along the top of the rectangular shape. They measure it basically along the hypotenuse of the right angles that are made by the frame. And it makes the TV sound bigger when they do that, because the hypotenuse is always the longest side of any right triangle. So that's a strange sounding word. We'll have some vocabulary here to look at in just a second. One of the links that I shared for this unit gives you a little bit of history about Pythagoras. He lived on the island of Samos, which is actually, I think now might even be part of Turkey. But you know, when he lived, you know, 500 BC, you know, the Greeks basically ruled all that part of the Mediterranean. And so it was not unusual for a person to identify themselves as Greek, even though they did not live in Greece per se. And you see right here in the second formula, his most famous theory, the Pythagorean theory. If you see this highlighted phrase here, Pythagorean triples? Anybody know what that means? Okay, it's actually one of my favorite things about right triangles. And coming from a math teacher, that shouldn't be real surprising that I would have something that's a favorite. But a Pythagorean triple, I probably won't be able to. Pythagorean, there we go, I think that's right. Pythagorean triple takes the equation a squared plus b squared equals c squared. And the idea that you have a triple here is simply that you've got three terms that fit a specific pattern that will always come out even. If you've ever heard of a 3, 4, 5 triangle, that is the most basic Pythagorean triple. So the long side, that's supposed to be a right angle. The long side is going to be 5. The next side is going to be 4. The hypotenuse is 5. I say that the short side is 3, 4, 5. So what you get when you square all those numbers, three squared is 9, 4 squared is 16, 9 16 is 25, 5 squared 25. Any set of numbers, any three numbers that follow that same pattern are going to be, they're going to be considered a Pythagorean triple. So if you take multiples, 6, 8, 10, that's a Pythagorean triple also. 6 squared is 36, 8 squared is 64, add them together you get 100, 10 squared is 100. It's kind of nice to know that you have these triples, because most of the time, if we're trying to find the length of one of these sides of a right triangle, they are not going to come out even, because you're going to have to apply a square root function in order to get a solution. But if you keep the Pythagorean triples in mind, even before you start to do a problem, that's the first thing I look at is this one of these patterns that's going to come out even? And if it doesn't fit the pattern, then I know I'm going to have to do square root function, and I should expect a funny looking number with a bunch of numbers to the right of the decimal. I mean, that's the main benefit of the Pythagorean triple. Now, there's some very famous uses of this Pythagorean triple back in ancient times. Does anybody know what I'm referring to? I don't know if I can draw this effectively or not. But if you take a rope with a series of knots on it that are equally spaced, 3, 4, here's the 5, 2, 1, 2, 3, 4. No, I didn't do that one right. Try that again. See, and this 3, 4, 5 relationship, this is another place where in history that Pythagorean triple comes into play. Pythagoras gets the credit for this, but I got to believe that it's been something that was known to ancient peoples long before he actually put the a squared plus b squared equals c squared into words. So he gets the credit for it. But if you imagine that this is a rope here, and all these dots here represent a knot in the rope, this is how they used to square up buildings. Somebody could stand at the side of a building at the wall and hold this knot here. It's at the top of this triangle, stretch it down to the ground. The next person would stretch it out to the fourth knot. And if it connected back to the beginning on the fifth knot of the rope, then they knew they had a 90-degree angle and they had the building or that wall was square. So it was true, it was plumb, whatever term you know. I think that a lot of this stuff was taught to slaves. So if you look at some of the ancient structures that are in Egypt and the Middle East and that area around the Mediterranean and Northern Africa that were built 3, 4, 5,000 years ago, they had to have known about this. And so a simple series of knots on a rope was something that basically anybody could be trained to use on a construction site. Nobody had to do any calculations. Most people didn't even know how to calculate anything back then. But you could train people to do this and come up with this 90-degree angle in that corner. So it's a kind of an interesting little tidbit of history. In fact, I have a book that my mom was a math teacher. I've got a book where it shows some of that. It's really a form of ancient technology in a way. And if I get a chance, I will try to scan some of the pictures out of there and post them in with the materials, because it's kind of neat. I mean, if we think we're so advanced and everything, but people thousands of years ago came up with this stuff, and they built monumental structures back then, gigantic, without cranes, without any kind of technology that we would recognize. So that's all you probably need to know about the Pythagorean triples. So let's get to the handout here.
I didn't see your car out there, Jay.
Cars are getting fixed.
Oh.
Getting 100,000 mile check today.
Oh.
Yep.
I thought we didn't have school today. I was like, wait, where's Jay?
No, we got 5 people on here already.
Oh, wow.
So the handout starts off with the Pythagorean theory. The thing about the Pythagorean theory that you have to be cautious about is identifying which side is A and which side is B. If you're looking for missing side links, because that's what this is about. This Pythagorean theory is used to find the missing links, the missing sides of a triangle. Anybody know what the sides are actually called? Think about that for a second. Did you want a hard copy of this again, Audrey?
Yeah.
The sides are actually called legs. A and B are called legs. The side of C, where C is, that's the hypotenuse. That's C is always the longest side. It's always directly opposite the 90-degree angle. So if you put that little square in the corner, print this real quick. Put that little square in the corner of your right triangle, you're going to be able to see it points directly at side C, which is the hypotenuse. So where the problem occurs is if you, like in looking at these problems here, the first two are relatively straightforward. I usually say the shortest leg is side A. That's how I'll label it. The other leg is going to be B. The hypotenuse is always C in the theory. So the first two problems here are pretty straightforward. They've got our X, our missing value is on the hypotenuse. So the first one, 8 squared plus 13 squared. $169 plus 64, that's 233. So that's the total, but that's not the length, that's not the value for X. A squared plus B squared equals C squared. In order to get to C, we have to use the square root function. So you're going to have to turn your calculator the other direction. The square root of 233 is 15.2643375224, etc., etc., etc. For us, in the instructions on these problems say round to the nearest tenth, so that would be 15.3. And that's the way most of these problems are going to generate your answers. So when you're finding C, that's the easy part. Hard to make a mistake on that unless you just mess up the calculation. Problems 3 and 4, though, you're already given C. They're giving you, I'm going to call that B, probably in problem number 3. Problem number 4, I don't know whether 19.1 is A or whether X is A. But you can't just put numbers in the positions where A and B are. Let's see, I don't know if that makes sense or not. So if I go back to my this whiteboard again, I got a triangle that's giving me 2 sides. Well, actually one leg, and it doesn't matter whether it's the A or the B leg. If I just go 7 squared plus 9 squared equals C squared, I haven't looked at the problem correctly. Because if this is the right angle, I already know what C is. C is 9. Okay, so this is all incorrect. So for a while, you might just want to work on getting the original equation written out. I'm just going to call that 7 value the A value. I don't know what the B is. They get labeling as X. I know that C is 9. So it's a little bit of a different equation solving exercise, because now you're trying to solve for one of the legs, not for the hypotenuse. It's no big deal. Just got to be sure your numbers get in the right place. So I'm going to subtract 49. Whoops. I'm sorry. I'm getting ahead of myself. So 7 squared plus x squared equals 9 squared. That's 49 plus x squared equals 81. Now I can subtract 49. X squared minus 9 is 2, 7 minus 4 is 3. X squared equals 32. So how do I find x? Squares and square roots are one of those unique sort of opposite operations. You know, from algebra, you hopefully remember adding and subtracting are opposites, multiplying and dividing are opposites. A square root is a special kind of division. A square with an exponent of 2, that's multiplication. So squares and square roots cancel each other out. Now, if I'm going to apply this square root, it's going to cancel the 2 here. Over here, I got to actually do the square root calculation. Is the square root of 32 going to come out even?
No.
Nope. And see, here's another place where there's some background information that can come in handy. Jonathan answered that right away. I don't know if you guys have heard me talk about something called perfect squares. It's a list. 1 squared equals 1. 2 squared equals 4. 3 squared equals 9. This is a good list to know. 4 squared equals 16. 5 squared is 25. 6 squared is 36. And the reason that they're called perfect squares is because if I apply the square root, they're always going to come out even. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5. If you've ever looked at a multiplication table, the numbers that go across the diagonal of the multiplication table are those perfect squares. And the number I got here is between 5 and 6. Well, why do I care about that? It's only a tool to help you estimate. If you think in your mind, okay, I know the next nearest perfect square is 36, so this has to be calculated, and it's not going to come out even, but it's going to be something less than 6. So if you do something on your calculator and you end up with 4.2, well, that's, if you've gone through that thought process, that should help you realize that you've done something wrong. So 5.65685, et cetera, et cetera, et cetera. That is the square root of 6. So that's 32, I mean. So let's say 5.7. And the thing about these square roots that we have to also remember, another thing is I can't just write 5 as the answer to this problem. because the square root of 32 is not 5. The square root of 25 is 5. So if you notice in the instructions, it's anytime you're dealing with square roots like this, it's going to tell you to round to something. The nearest tenth, the nearest hundredth. The more decimal places you include, the more accurate your solution is going to be. Because you can't just round it to the next whole number, because you're misleading people about what your answer is. You know, I can't say it's 5. I can't say it's 6, because those are the result of perfect squares being square rooted. And I don't have a number that's going to be a perfect square. Questions, anybody? Okay, hang on for just 1 second. So that 30.5 is always going to be C. So if I'm working these problems, that's the first thing I'm going to try to identify. I want to be sure I understand where the hypotenuse is. Okay. So once I know the hypotenuse, I've already got one of the 3 terms in the equation sorted out. I know that for number 4, 30.5 is going to be C, and I'm going to have to square that. What about problem number 5? I don't see any right angle symbols. What kind of a triangle is that? The big triangle. We've got some congruency marks there. So that's a clue right there. What kind of triangle is the triangle in number 5? Which of the classifications that we've talked about has 2 identical sides?
Equilateral.
No. Equilateral, all the sides are the same. All the sides are the same. All the angles are the same in an equilateral triangle. This is not equilateral. We don't have all 3 sides the same.
Is it isosceles?
It's isosceles, right? And so where we show X here, this goes back to the last unit. That dashed line that's going straight down to the base, that's what's creating your 90-degree angle. That's the altitude, right? So no matter whether you figure that this side, you got a right triangle here on the left of this dotted line and a right triangle on the right of that dotted line, how would you set up the equation? Are you going to use 22 in the equation? I hope not. Because overall, that's an isosceles triangle. It's not a right triangle. So what are you going to use for A? If I only look at this part here of this triangle, from that dashed line to the left, what number am I going to assign to that piece of that triangle so that I can do this calculation? It's not 22. 22 is the length of the entire base. So how much is that portion of it that I have highlighted?
11.
Yeah, it's half. So your equation is going to be x squared plus 11 squared equals 24 squared, because the 24 represents your hypotenuse. If I draw my right triangle box right here, it's probably what you should do if you're trying to solve this problem. Like I said, identify the hypotenuse first.
Is the answer for number 4 23.8?
23.8. Let's see. Absolutely. Very good. Good job, Jonathan. So, if you look at number 6, I mean, anybody have a question about 5? How to approach that? Got another idea on how to approach it? What are you going to do with problem number 6? How are you going to figure out what x is? I need to create a little Jamboard thing here real quick with this problem to show you. You guys think about that. So here's that problem, number 6. I see 2 different little squares in the corner of that shape. It's a 4-sided shape. Where can we identify a right triangle that's going to allow us to figure out what x is?
Can you bisect it?
What are you gonna, can you explain that? What are you thinking there? Bisecting it how?
I don't know. I was just throwing it out there.
Okay, well, that's a good start. You're going to have to be able to visualize lots of problems like this, because that's how they're going to try to make these Pythagorean theory problems more difficult. Anybody else have an idea? See right triangle now?
Yeah.
So since I made sure to create a rectangle, this side here of this newly created right triangle is also going to be the same length as x. It has to be, because it's a rectangle, right? The parallel sides of rectangles are equivalent, which also means then that this little piece of this top side is 5, because that's what this is. So the remainder of this upper side now is 13. Because the total length of that top part of this shape is 18. All I did was carve out a part of it here so that I can use the Pythagorean theory allows us to use. So the 16 side is going to be my right, or it's opposite the right angle, so that's going to be my hypotenuse. I don't know which one of these is going to be shorter, so I'm just going to say x is the A side 13 is the B side. 16 is the hypotenuse. That one's obvious because it is opposite the right angle. I mean, are you guys okay with me drawing these two right angles up in this spot here? I mean, if it's a right angle on the right-hand side of this line I drew, this line right here, it has to be a right angle on the other side too. Otherwise, it's not a straight line. I've done something wrong, or the universe has totally shifted on us. So 13 squared is 169. 16 squared, I want to say 264. I know my perfect square is up to 15. It's a little fuzzy after that. Yep, see, I had it wrong. 256. 256. That makes sense, the setup? Where I came up with those numbers? So once I take the 169 away from both sides, I got x squared equals 87. Is that a perfect square?
No.
Nope. The next nearest ones, 9 squared is 81. 10 squared is 100. And what I usually encourage people to do is at least learn them up to 12. If you can learn those squares up to 12, that will help you a lot with all kinds of different estimating. And believe it or not, if you ever work in any kind of production facility where things are counted in a gross, there are 144 things in a gross. 12 squared, 12 dozen eggs, you have 144 eggs. It's another way to remember it. So now I've got this x squared equals 87. I know my answer is going to be somewhere between 9 and 10. .327. So x equals 9.3. Huh. Doesn't really look like it the way that that's drawn, but I'm going to have to trust it because that's the way that it calculated out. Anybody have questions about that? Okay, what are you going to do with problem number 7? Got another right angle here on either side of that line, that vertical line that says it's 12. X goes across the entire base of that big triangle. Really got 3 triangles here. Only 2 of them are right triangles though. So can I just say 14 squared plus x squared equals 29 squared?
No.
No, I cannot. Because this big triangle with the 14 and the 29 and the x, that's not a right triangle. There's nothing there to indicate that it's a right triangle. So how am I going to figure out what part of x or what parts of x I can use to calculate? Am I only going to have to do the calculation once to come up with x? Well, that's just a different way of asking the same question that I asked a minute ago. Can I use the 14, the 29, and the x and say that's a right triangle and use a squared plus b squared equals c squared? No, I can't just do one calculation. This is a multi-step problem. So what would you do first?
It'd be 12 squared plus x squared equals 14 squared.
I'm with you there. The only caution, you're not talking about all of x, are you?
No.
Yeah. You got to remember that for that right triangle that's on the left, you're only going to find this portion of x. So maybe call it x prime or x to the x1 or something. So 12 squared plus x squared equals 14 squared. Okay, there's your first calculation. Now what about the second one? How do you figure out what the rest of x is? How do you figure out what the rest of x is? Okay, so what Jonathan just told me, told all of us, here's where I started with the other right triangle symbol. We're gonna find this amount of x first. That this little piece right here, probably call that a. Normally a squared plus b squared equals c squared. So it's part of x. It's not the total amount of x. But he said 12 squared plus, let's say that's the first x, equals 14 squared. So we're going to call that x1. The other part, x2. All the rest of that. So how do we come up with the calculation for that? Do I have another right triangle I can use?
Yeah.
Sure do. Here's the hypotenuse. So that's going to be C of that one, the triangle to the right. So what should our calculation be for that one? I'm still going to use the 12. I'm not using the 14 on this one because that's not even part of the second right triangle. 12 squared plus the remainder of x squared equals 29 squared. So two calculations are necessary on this one to help you figure out what overall x is. It's the same calculation, two different triangles. Just another example, you can't just automatically start throwing numbers into the Pythagorean theory. So is 144 plus x squared. And that's 196. So the first little part of x squared is 52. 196 minus 144. I think that's right. Yep, 52. Square root of 52, not a perfect square. The square of 7 is 49. Square of 8 is 64. So it's going to be between those. Square root of 52, 7.2. So that first part of x is 7.2. So I'm going to pause this now and give you guys a minute to do the rest of the calculation and figure out what the rest of x is. And once you have an answer, put it in the chat just to me, please. Don't say it. All right. Well, if I had a prize to give, I would give it to Jonathan today because he got the second calculation correct. 26.4 is what x, the second part of x equals. These numbers get pretty big once you start squaring them. Square root brings them back down to size. That's actually the square root of 697. I have no idea if that's a perfect square or not, so you have to use a calculator. Square roots are always pretty much going to be like that, unless it's a perfect square. So how much is the total length of x? Now you got to add those two pieces together. 7.2 plus 26.4. 33. Oh, that's a nasty looking 3. Sorry about that. $33.6. That's how long the total length of x is on the overall large triangle. So I know you guys probably remember me saying you have to work with what you're given on these geometry problems. You can't force something to fit. And so if you looked at this problem at first and you thought, oh, here's my right angle, there's no way you would have gotten the correct answer. Because that's not, there's nothing on this drawing that shows you that that would be a right angle. Because if you thought that, you would just do 14 squared plus 29 squared equals x squared. When it doesn't fit, it's not a right angle. There's nothing to indicate that it is. See, it might look like one, and maybe it actually is if we had a way to measure it, but we don't. So don't try to force it to fit. But you're going to have to use an analytical strategy to figure out these multi-step problems and figure out, okay, where are some right triangles that I can work with? And you'll see that on these other problems in the handout also. Okay. Going to have to do multiple calculations here on number 8 and maybe multiple calculations on number 9 with this trapezoid. It's actually an isosceles trapezoid. How do I know that?
Because they're parallel triangles. Or they have a...
What's these little tick marks telling me?
It's
Congruency. It's congruency. So we got two sides of this trapezoid that are equal. The overall length is 40 of the base. The top part of this is 26. So with those two numbers, 40 and 26, I can easily figure out how much this little piece over here is and how much that little piece is. It's going to be the same because it's going to split it. This is a rectangle that's 40 by 26. Excuse me, 26 by something, 26 here. So 14 has to be split between these two other pieces. So this little one on the left is going to be 7, and so is that one. So now I have information on both of these right triangles that are hanging on the end of this trapezoid. Questions, anybody?
You really only have to do one calculation on the number 9, right?
Looks that way to me, yeah. Yeah, once you realize that the difference between 40 and 26 is being split between this little segment over here and this segment over here, they're going to have to be the same. You got the right angles there shown. So you know that the 20 is going to be the hypotenuse of this triangle, and over here it's congruent, so that's going to be 20 also. So you got 7 squared plus b squared equals 20 squared. Now, these next few problems here, these are classic right triangle problems. And it says, right in the instructions, draw a picture, then solve for the missing side. Round your answer to the nearest tenth. You will see problems like this on the test. A roofer has a 16-foot ladder. The base of the ladder is 5 feet from the house. How high up the house does the ladder reach? How do you know where you should put those values? Unless you do a drawing. So I got a house. It's on flat on the ground. So I know that's going to be my square. That's going to be the right angle. It's not the Leaning Tower of Pisa. It's a house, a regular house that has vertical walls to the ground, perpendicular to the ground. So 16-foot ladder, and I don't even care if the drawing fits what it would actually be like in the real world. I don't know if that's representative of 16 or representative of how far up that ladder goes on the house. That's what we're going to try to find. The only other number I got is this one at the bottom. It says the base of the ladder is 5 feet away from the house. So if I were to think about this a little bit more, now that I know that's only 5, if I want to be a little bit more accurate, then probably that's a much skinnier triangle in reality. Doesn't matter. The drawing is there just to help you understand what the problem's asking you to complete. And we have a winner, 15.2 feet, because now you got 16 as your hypotenuse. The 5 is the A side. So what you're trying to solve for is the B side. So Jonathan dove right into that, got an answer. Let's see how correct he actually is. Oops, too far. 15.2 feet. See, these drawings aren't any better than what I just made. And it doesn't matter. Who cares? It's, remember, geometry, very visual, because it's all about shapes. So take advantage of that. Use what you're given here. Number 11 is kind of similar to my television question earlier. How do they measure the size of a TV screen? Well, it's across the diagonal. The jogging problem, Ashley there. Pretty common also. If Ashley starts here, this dot, which way is east typically? If you're facing north, east is going to be to the right. It's going to be on your right hand. And so she jogged 3.4 miles and then went immediately 5.7 miles to the south. Okay, on that one, 11 and 12, both of those, you're trying to actually find the hypotenuse because that's the diagonal. See, this is another reason why we have to use the distance formula on graphs when we're trying to find the diagonal, the length of something that is diagonal on a graph. Remember I said before, the distance formula is just a modified version of the Pythagorean theory. So hopefully now that's making a little bit more sense that you've seen a few, how a few of these problems work. Problem 13, a 31-foot support wire is attached to the top of a 25-foot telephone pole. Now you're trying to figure out how far the pole is from where the wire hits the ground. Okay. Well, it's still a squared plus b squared equals c squared. Got to make sure that you're putting the unknown in the correct place in the equation that you create. If you notice 11 and 12, the unknown is the hypotenuse, so you put the x out here where c goes. On 13, it looks like whoever did this teacher's edition decided that x was going to be the b side, and they used the 25 for a. Okay. That part of it doesn't matter, but don't try to put it in where the c goes, because that's going to give you a wrong answer immediately. Questions, anybody? Okay, and I'm going to have to stop at this point because I'm going to go as far as seeing who remembers the acronym for trigonometry. You know, if you know these words, sine, cosine, and tangent, trigonometry, trigonometric ratios. The word trigonometry means measurements of triangles. So with relationships between the sides and the angles in these right triangles, we can create some equations that follow specific patterns, and you'll be able to figure out the sine, cosine, and tangent. And to remember it, you want to remember the expression Sohcahtoa. And I'm going to have to find it because it's so here are the notes that there's no way you can do trig ratios unless you remember these relationships. So make sure you get all of these relationships in your notes. Here's Sohcahtoa. When you're trying to find the sine, if I'm looking for the sine of angle A, it's the opposite over the hypotenuse. So here's the side A, here's the side C, which is the hypotenuse. That's what Sohcahtoa tells you every time how to find one of these calculations, whether it's sine, cosine, or tangent. Sohcahtoa is very specific. So sine is the S, opposite is the O. Opposite means different things depending on the angle that you're standing at. If you're standing at where angle A is, you're looking across the triangle to side A, that's the opposite. Again, hypotenuse is always the hypotenuse. So you got to remember that. If you're standing here where the letter B is, the large capital B, and you're looking across the triangle, now side B is the opposite. So the orientation determines what's opposite. Now, sine and cosine both involve the hypotenuse. So if you can identify the hypotenuse, you're headed in the right direction. So cosine is the adjacent side over the hypotenuse. So if I'm at A, again, the adjacent side's connected to it. So that's side B. And I'm going to divide that by the hypotenuse. That's what all these letters over here are telling you. B divided by C. Change my orientation and go down here to find the cosine of angle B. Now the letters are different for the sides. Toa, meaning tangent. It's the only one, again, that does not include the hypotenuse. It's opposite over adjacent. So make sure you have those in your notes. I heard somebody take a picture of it out there. That's a good idea. You really need to have this filled in. And be sure that you remember Sohcahtoa. Anybody have questions? Because we are pretty much out of time with that. There's way more stuff that we're going to have to do with tangents. All righty. I'm going to let everybody go, and we'll see everybody on Thursday. Send me a text if you need some extra help, okay?
How many more? We only have 2 weeks left, right?
Grades have to go in the Friday after Memorial Day. So I think it's actually 3. This term's a little bit longer. So we have all the rest of May, plus the beginning part of the first week of June, right after the holiday.
Okay, cool.
Yeah. So the final will be that last week after Memorial Day. Assuming we can get through all these, it should be, maybe we'll even do it on Tuesday that week.
Right on.
Okay. See you guys.